Hello, everyone. My name is Darwin. I work out of GitLab's Field CTO office. I wanted to talk to you about a couple of important embedded DevOps topics. The first one is something that everyone's really excited about, hardware in the CI loop. Being able to take embedded development and move it to much more scalable architectures and widen that bottleneck of having to eventually test on real hardware. The second one is very important as well, but the first one kind of obscures our vision of it, and that's the transformative power of sharing work in progress. Embedded development has by necessity been a relatively isolated activity, and in order for you to get the full value promises of Agile and DevOps, you need to have shared work in progress. So let's get started. In 1984, a brand new video game was born out of Russia, and that game was Tetris. So if you go back far enough, you may have played this game back in the day, or you may have been playing it very recently. Interestingly, Tetris took 36 years for humans to dominate it. And by dominate, we mean that the high score counter was never wrapped until quite recently, and the gameplay levels that were considered impossible at one time are now possible and regularly achieved. So the question behind this is why? Why would it take 36 years for human domination of Tetris? It boils down to something pretty simple, actually. At a certain point, as the internet emerged, Tetris predates widespread internet usage. There was a gaming board site that would keep track of the highest global scores. However, in order to prove that you weren't cheating, you had to turn in videos to ensure that you weren't running the game by another computer. Those who were trying to achieve this in Tetris would have to turn in a video that showed their hands as well as their score and the game board at the same time. Now, this inadvertently allowed transparent sharing of their methods. And as they shared their methods, we had an agile transparency that was enforced by the very necessity of trying to have this gaming high score be global. And so this was a very interesting effect, and it is cited as an aspect of how humans, when they work together and share their work in progress and their work methods, they make a lot more progress in certain key important ways. And, it all kinds of starts with all of us with the concept of sharing your toys, right? So in this case, they're sharing videos, but we're taught to share our toys, and it's fairly frequent that the concept that we get from this is, well, if I share my toys, then I'm going to learn to be generous, and that's a good and moral lesson. So I will allow others to use my toys as well. But there's something else that's much more important. It's not actually that we just learn to share, but there are many wonderful benefits to sharing. So in the case of sharing, we end up moving from an isolated practice or an isolated capability where we're learning and building and understanding to sharing our work in progress. So instantly by sharing our toys, in most of these situations, we're in the same place and we can also observe what someone else is doing. And eventually that gives the opportunity for collaborative expertise to be built because we might start working together on how to build things. I think that it's really important that we take this simple childhood lesson. We understand that the real benefits of sharing go far and beyond just the moral lesson of it's great to be generous. So I want to kind of bridge this concept over into how we take DevOps and Agile and apply it to embedded development. And the reason I want to do that is because embedded development has been, by necessity, a fairly isolated practice. And that comes down to the basic necessity of attaching to hardware. Frequently, this is done at the desk, and the individual developer has to develop against that hardware in isolation because of the fact that they need to be in that environment. It's not that there's no collaboration going on. It's just that the dominant focus is to getting one's work done at your desk. The other factor that comes in is when we test on real hardware rigs, it can be extremely expensive. As you know, a hardware rig might be a prototype that is worth hundreds of thousands or even millions of dollars. And so that real final test always kind of bottlenecks us. And so this reality of embedded development has caused it to be a fairly isolated practice just by de facto momentum. Now, one thing that's really interesting too is with the entrance of AI to all coding has some real opportunities. In the case of embedded, I've tracked a couple. One is learning Rust or upgrading your code to Rust. We have a couple blogs at my company about doing exactly that, learning Rust with the assistance of AI. And there are a lot of other things it can do for you, helping you with building unit tests, helping you in a lot of activities. However, as long as we've got the hardware bottleneck, we end up with AI only making this problem worse. One of the other problems here is that we're not only isolated, but we have this slow feedback cycle, especially if that last step is shared. So what we want to do is use the technology of DevOps and Agile to expand this bottleneck and make it a better story. So we'll talk a little bit about how that happens. In this case, we're just going to consider that AI is already accelerating your coding. And so whether you're AI accelerated or not, this will help speed up your development process. One of the things that's been around for quite a while is CPUs that are compatible with embedded. So we have cloud scalable ARM CPUs. Also, if you've been doing cross-compile, of course, there is cloud x86 compute for a long time now. And so there's been the ability to do embedded builds for quite a while in the cloud. Simulated hardware is another great area, and this is becoming more and more common. There are, of course, third-party companies that have been doing simulated hardware for quite a while, but now a lot of vendors who come up with hardware are very understanding of the fact that you need to accelerate your processes. So they're more focused on ensuring that you have some sort of simulated platform to do your initial testing, prototyping, and ideas on. We have the concept of testing on real hardware, but something that's not the full rig. So sometimes this is called processor in the loop or FPGA in the loop. And it's basically the idea of taking a hardware that's somewhat representative of the real thing and ensuring that we test on that early or prototype on that. Another aspect that you'll see in some tools and products is something called environments as code. And environments as code is the ability for your system to set up these simulated environments automatically and to destroy them automatically. So this is kind of integrating the whole environment deployment. And when we have simulated hardware and even real hardware, we can now allocate and deploy to resources as part of a pipeline. And so this is a very interesting capability. In the case of GitLab, these are lifecycle managed environments, which means as soon as you open a merge request, that opens a branch, and the opening of that branch causes any environments defined for it to be deployed. Then as you update your code, any changes to the environment building code are pushed to the environment. But most importantly, when you merge your merge request and delete the branch, the environment's destroyed for you. And this is a really important step. One organization I work with by enabling developers to create environments, but there was no natural way to know when to delete them and remove them. They ended up with 10x spend in development environments than what it took to support production. It's a very cool capability, but it has to be a managed capability where the entire lifecycle loop is closed so that you don't run into a situation where you have a lot of environment sprawl. And then finally, testing on 100% accurate hardware. Notice that on the third and fifth items here, I have something listed called Device Cloud. This is something that I've simply built as a GitLab CI/CD component, which allows you to create an on-premise cloud of your own devices. When I talk about this, a lot of people get confused that I mean that somehow it's attaching to the public cloud, and it's not. I call it a cloud simply because when you deploy your own devices in this arrangement, they are a pool of available devices, and when a pipeline wants to use one, it can allocate it, have exclusive use of it, and then when it's done, it can deallocate it and release it back into the pool. So just the basic idea of a cloud of devices that everyone can share and use. So what this does is helps us speed up this feedback loop. Now, one of the resistances I hear is like, hey, there's a lot of work here in getting all these intermediary environments. I think we might do this, but we're just going to put the 100% actual hardware in the loop and skip all this intermediary stuff. But it's really important to realize that although there's some effort in getting this initially configured, that fast failure is a form of productivity, and it's also a form of widening bottlenecks. Let's say we have a math mistake in our code, and instead of our code all having to wait for 2 weeks so we can get on the $500,000 unit and run it to find out we have a math error, we can discover that in a much cheaper environment that's scaled more broadly. So when you look at this green path here, all the environments to the left can be scaled more broadly, in some cases and scalable if you're putting them on an actual public cloud. Just keep this in mind that fast failure is not just a fast feedback mechanism, which is super helpful. It is also a mechanism for reducing the pressure on shared resources, as well as for developers to be more productive because they get feedback that can be achieved at a cheaper level much quicker. For a lot of organizations, I hear this looks like heaven on earth, and they really want to get to this place. And it's important and it's necessary. One of my concerns, though, is that if we dust our hands and stay there, it's still possible to automate all of this and be isolated. And the problem that I have with that is that it isolates us from some other value promises of DevOps. So DevOps purports, and Agile purport, to deliver value in the areas of people, process, and technology. And this green box is really only just technology. So it's important to go beyond that into shared work in progress benefits. Once we have this shared technology stack, all of the information coming out of this testing can flow back to a shared work in progress mechanism. And that mechanism is going to be your merge request. And inside of this, we are able to share in a lot more important things. Shared work in progress allows us to build expertise across our team, but it also allows us to innovate at the product or the customer level. When we can share that human expertise about how to build a better solution for the customer, we start to get more real innovation. And I'll talk about some stats here in just a minute. Another aspect is shared workflow. One of the interesting things is, as technicians, we always want to make everything into pure machine automation that we can, because that removes human toil and moves that activity to a resource that's less expensive. However, there's almost always some remaining human tasks that must be done. And if we're not careful, we don't realize that we can apply a lot of automation to those as well to make those smoother. And this is known as workflow automation. And so within GitLab, you have a lot of flexible tooling and capability to create a flexible workflow that matches what you need to do. The other concept is shared governance. So some of you might be dealing with functional safety aspects of a product. And when you have to deal with functional safety, there is a lot of governance. And so in being able to put that governance inside of a shared in work progress system is a great way to tighten up some of these loops. In GitLab, we have the ability to block merge requests if the developer is accidentally introducing some new security findings and didn't realize that the latest version of XYZ board support package has a vulnerability in it, or any other number of ways that you can accidentally add vulnerabilities. Also, these are enforced as a matter of policy on all projects, as opposed to having to be dealt with on a per project basis. Shared AI. So you'll notice that while some AI is available for code generation, which is an important aspect, there is also AI available for a lot of other aspects of development. And if you pay attention carefully in the industry, this is frequently inserted where you normally collaborate with humans, that you interact with AI in those places. So when you don't have a shared work in progress practice, you also have less AI available to you. Another aspect is shared software build and test expertise, or what I call shared software manufacturing expertise. If we imagine for a minute that we're building a toaster, and I don't mean a smart toaster, just a regular toaster, in the upper left corner here with the shared human expertise, we'd have our 25 engineers who make and focus on getting the world's next greatest toaster. And once they've created that toaster, they are then going to plant engineers and say, we need a plant either created or configured to build this toaster. And in physical manufacturing, we recognize the difference in specialty skills between these two groups. But sometimes in software, we try to force all 25 of those toaster engineers to become toaster plant making engineers. Within a shared framework, there's a capability to create shared aspects of the software manufacturing plant. In GitLab, this is CI/CD components, and it allows a few specialists on the team to create the CI that most everyone else uses. And so that's a really important aspect, is the ability to encode software manufacturing expertise into your system and share that among your team. Finally, shared visibility. Increasingly across all software realms, the question is being asked, how much business value for the company or customer value for our end customer is being created by software activities? and that's known as, loosely as value stream. There's a bunch of ways of measuring this that cause everyone in the organization to focus on customer outcomes and customer value. Embedded can also have this benefit of emitting this signal to the company's leadership and to customers that we're focused on customer value. But this is also shared visibility. So that shared work in progress has to flow into this area for that to be the case. So when we talk about all the wonderful ways in which sharing our work in progress can benefit the organization, I just want to highlight that, back here at the workstation, we have isolated development by de facto momentum. And what that means is we can get really excited about getting the access to the bottom layer here where we have the green arrow, and we can be really happy that we've saved a lot of money, we're more productive. But then because we've always been isolated, we continue with our cultural momentum of being isolated in our work in progress when it's no longer necessary. So while the bottom helps us to share some very important aspects of software development, it also is sort of a feed in to being able to share a lot more important information about our progress. The bottom is shared technology, and those are cool benefits of DevOps. But if you feel like you're not getting the full benefits of DevOps, perhaps you're not sharing enough work in progress and changing your systems to do that. You can kind of think of it as this first step is towards shared technology, and then that enables a stronger step towards shared customer innovation through the shared work in progress in our development process. It's important to realize, though, that you don't have to fully implement this bottom green bar to get all the benefits of the purple box. So you can approach both at the same time, and you can even go for some purple box side things before you've got, the green box, the green arrow solved here. So while I'm depicting them as somewhat dependent because I feel like a lot in industry will go through it in this way, it's not something that you have to approach this way. You can approach both at the same time. One analogy I like to show is this concept visually of workstation isolated development is sort of like car manufacturing used to be. Engineers who are working on new features are going to have a unit each to themselves. Even though they can collaborate in this environment, the tendency might be to work and get your stuff done and to not to collaborate. Interestingly, when we move to a collaborative shared work in progress approach, we start getting some huge benefits of sharing. In this case, we're sharing the resource of this wind tunnel, and we potentially have a lot more human collaboration going on because we have a much more shared process together. Just want to quickly talk about some of the benefits of feedback. These are all some of the benefits of feedback in digital photography. So it's amazing that the whole concept of photography in the world has changed so massively just because digital photographers can get that feedback. And I experienced this myself, had some interest in film photography when I was younger, got back into it as digital matured. And it is quite amazing how that closing that feedback loop can cause a lot of innovation just within the one person's skills and a lot of expertise building. So that fast feedback is a catalyst to that expertise creation, just even within an individual. But I also want to move on and talk a little bit about expertise creation by the sharing. So these are 8 different studies that talked about the enhanced capability of collaborative work. And so you can see here, acceleration of learning and skill development, 23%, enhanced problem solving abilities, 63%, increased innovation and creativity, 28%, faster error detection and correction, number 6 there, 35% faster, enhanced knowledge retention. So there's a lot of information about how collaborating on work in progress is a massive benefit to your team and to your company. This will be in the slides that you can download. I just wanted to cite the studies. Notice these are not studies, really super recent studies. So these studies really predate the adoption of Agile and DevOps capabilities within the regular software industry. Just want to touch a little bit on the device cloud. The device cloud capability is something that's a CI/CD component. It's really a community component maintained by me. So just be aware that it's just a very highly capable community component. It is not baked into GitLab per se. Although, like all platforms, when you have an extensibility capability like we do with CI/CD components, there's still a ton of value that's added by something that is built as a component. Basically, it allows you to take your hardware units wherever they reside. They could even be on people's desks and group them into a shared cloud. If they're on someone's desk, then you'd want to make sure they know how to offline it out of the shared pool if they need to use it in a dedicated format. But you can see how this sharing would help a lot. I'm just going to walk through a scenario now that is theoretical. It will help you kind of understand how we can just share a lot of expense and reduce a lot of expense. So just giving an idea here that let's say that we have a bit of hardware that's worth $1 million per unit. And to maintain a reasonable cost profile, we've bought 4 globally. These are some Goldilocks inputs, right? But you can take this model and refactor it for what you actually do. Let's say these are spread evenly across time zones around the world. And we'll assume that we get 40 hours of utilization per unit per week. And I'm calling this generous because we're assuming this is a manually scheduled system. Humans have to talk to say, hey, it's your turn to get on the hardware. I'm done with it. There's a spreadsheet or a person. It could be generous to say we get 40 hours, or we might be getting 40 or more hours because this is such a painful situation that people will come in off hours to get access to the hardware, kind of like the old mainframe days. I've heard stories of people in the mainframe days coming into work at 2 a.m. because they could get so much CPU to do their work. However you slice it or cut it, if this is a manual sharing mechanism, it's going to be fairly inefficient with regard to machine utilization. We'll say we have a queue of 12 engineers that have to wait about 4 weeks. We're going to put their average total comp at $300K, which could be low or could be high depending on the market. If we do a calc here of annual productivity loss, people are roughly waiting for $3.3 million a year worth of waiting to get their tests done. And they might do that wait more than once, but this would be kind of our annual run rate. So our utilization of the resource is approximately 24% if we're at 40 hours a week versus 168 hours a week per unit. So if we start to break down our process and to start to widen this bottleneck, we're going to talk about some of the impacts of that. So what we just went through was the model of how that end device on the right-hand side is very expensive and very limited and has to be scheduled. This is just acknowledging that the humans in the loop are the most scarce resource. So sometimes we think about $1 million machine. Wow, that's a really important and scarce resource. But your people's time to be productive is actually even more scarce and even more important to the overall strategy and competitiveness of your company. The first way we could potentially achieve a lot of savings is simply by using these 168 hours a week. But this does require automation. It not only requires automation in order to facilitate the everyday so that there's no time lags between hardware usage, but also if we want to use it all weekend, if we can queue up work that will wait during the weekend and get processed, we can use that weekend time as well. So that's why you have to really think about the fact that an automation week versus a person week is very different because automation doesn't need to rest, doesn't need weekends. So if we could simply boost by 168 hours, which is, potentially also a little bit optimistic, but we'll push the model that far, we could reduce our cost by 76% because we get 76% more utilization. So that saves $2 million of the $3.3 million of productivity loss. Another aspect is starting to offload some of our tests to failing faster. We don't get full test coverage. So this gives a scenario. I'm not going to read through all the details, but it gives a scenario where we could get 80% test coverage in a hardware processor that's somewhat like the final processor or the final embedded assembly, however complex that is. So if we can do that, we can save another $400K. So, we're starting to really squeeze this number down because when we fail fast, that test never gets to that final machine. So it's a literal savings. A lot of this is really basic stuff covered in the, now ancient book called The Goal, which was much more about physical manufacturing plants. But when we look at our software manufacturing plant, any constrained resource behaves identically to that book. A little further, if we can do fan-out testing. In this scenario, we're saying, hey, by the way, the hardware interface to this unit or the software interface to it, it can take more than one test at a time and process more than one test at a time. And this, so you can fan-out test things in a pre-production or non-production software model and get your tests to go wider, which means that they can fail even faster. So we can potentially have another 300K of savings. I've gone through this exercise. This model is something that I just sat down and built out. So if you find errors in it, I would love to hear from you. I know there's a lot of variations, and a lot of these things, you might have to downgrade their Goldilocksness, but that's okay. It will still help you with a framework for understanding how you might save hard dollars on shared hardware costs. I want to transition now to a little bit of a demo of how we see this in GitLab. Right here in GitLab, I am in a merge request. And a merge request is the single source of truth for a developer who's making code changes. In GitLab, we can configure our environments as code so that every time you create a merge request, which requires you to create a branch, you get an environment that's specific to your setup. And so I want to show you how some of this is working. The hardware behind the scenes here is a Raspberry Pi Pico W, which is a microcontroller. And then we have in the middle of that a hardware gateway, which has to be able to run full GitLab. I chose the Raspberry Pi 4 and 5. I want you not to get too hung up on the hardware. This is not specific to the Raspberry Pi boards. It's not specific to any board. You could use any board for the gateway, for the runner gateway, and you could be wiring it to any board or board assembly that is a microcontroller or a embedded setup of any type that you can wire in. So if you can wire it to your desktop, you can do it in GitLab. If you had to, worst case, and I have seen this with Windows, you could run a full-on desktop as the runner gateway. I know that embedded development is very board specific, but the model that I'm showing you here is not tied to the specific hardware. It could be implemented many ways. Let's just dig into this pipeline here to see some of the aspects of virtualizing this. So I want to focus on the deploy stage here. And right here, we have Walkwe SIL, or software in the loop. Walkwe is a platform that emulates many small boards in the cloud. And so this is adopted to Walkwe's CI support. We're going to dig into this log. And we can see here that we are running Walkwe's CLI, which is right here. And that Walkwe CLI is processing this particular settings file. And that causes it to upload the firmware from the actual build we're doing in this pipeline. So the firmware was built by an earlier stage. We upload it to the emulation platform. And then we also use this particular test file here that configures tests for Walkwe's platform. And we see here that our simulation was started and we got the expected result from the serial interface. It also outputted a log file and we collected that log file. So if we go back, and if we go back to the merge request level for a moment, that was also exposed. So in GitLab, there's a keyword in CI called expose as, which allows you to expose any CI artifact that's collected inside the merge request. So if I was to click through on this, I'd find a log file that just says LED on, LED off. Dig back into our pipeline, and I want to show you right here, we have this Walkwe human in the loop environment deploy. Walkwe also has the capability to deploy a graphical environment. And this is human in the loop. Many organizations, you do need human in the loop if your particular situation has a GUI. But the environments don't have to deploy human in the loop. You might have a complicated setup where there's like 3 or 4 virtual ECUs and it takes automation an hour and a half to set it up. That would be perfect for environments as code as well, even if a human never opens them. I wanted to show you, though, that this can be used for the most challenging case, which is to have an actual graphical environment. So this is the deployment job, and this is the destroy job. The destroy job, if you have high enough permissions in GitLab, you can destroy the environment and then rerun the branch, and it'll recreate it. So if you suspect the environment is kind of like, I think it's compromised, it's got some goo in it, you could reset it. The other time that the destroy is used is when you do a merge delete to clean up the environment. This is super interesting that it does the life cycle like this, because when you have this destroy job, there are 2 important process signals that you receive and can validate at that time. One process signal is it okay to delete the environment? One thing you run into with managing developer environments is, if you get too aggressive and you're like, this environment's been up for 6 months, it's cost $1,000 over that time, I'm going to destroy it. And then you find out it's being used for a customer demo the next day. So the signal of whether it's okay to destroy an environment is important. And the other aspect is who can say that it can be destroyed. And so when a developer does a merge delete, they're done with their code. Whether they decided to not use the code or use the code, they're done with the code and they're done with the environment. Sometimes they hear the pushback, well, developers won't let us destroy their environments because, and really the because is because you've made it really hard for them to create them because they never clean them up, which ends up being a really negative cycle. So in this case, we have both signals that we're done with the environment and the developer is ready to destroy it. In general, developers will not resist environment destruction if the way to create a new one is you just create a new merge request and no humans and no forms are involved and a new environment is deployed. So just think about that you're going to have a lot less resistance if it's a completely automated process. So because this created an environment, I can go down to Operate Environments. And right here, I have just the one environment. But if I, as an individual developer, had 3 things under development that are different, I'd have 3 environments. If there's 8 developers working here on 8 different projects or 8 different merge requests, there'd be 8. And right here, you can see I can stop it. I can also replay it or rebuild it or update it. You can see here what was deployed to it most recently. And then I'm going to open the environment. And inside of WalkWe, we load up our current code on the branch, and I can play it. If I was to update the branch and push to it, say I pushed 5,000 milliseconds instead of 444, then when we came in here, the next time it would say 5,000 here. I'm going to push play on here. Right now, this version of the environments is uploading that code and building it in WalkWe. The next version of this component is going to upload your firmware. So you won't need to press the play button. It'll just start playing automatically. So that's both environments as well as the concept human-in-the-loop testing. Finally, I want to show you right here that we have hardware-in-the-loop testing. So hardware-in-the-loop, this is allocating out of a pool of 3 Raspberry Pi Picos that are managed by the runner gateways, as I mentioned. It doesn't process these in this order. Unfortunately, when we do it this way, it mixes up the order, but it does an allocate of a device. It then runs a child pipeline and then does a deallocate. And over here in the child pipeline, we can see what happened. And I'm going to open up the log so we can see what happened. And here you can see that we flashed the device. And so we're prepared to do our next job. Because this particular runner is locked to my pipeline, if anything else tries to run on it, it gets evicted. If someone doesn't follow the component and use the component properly, and they accidentally try to schedule over you, it gets evicted. And then also notice that we're only doing hardware in the loop where we need to. So if you have permanently allocated devices or any mechanism that allocates a device at the beginning of the loop, this build stage takes a long time. So I don't need to be holding the hardware during that time. I only need the hardware down here, so it also only runs when I need it to. So that's some of the aspects of the software automation. I want to show you some of the aspects here, though, of shared work in progress. So one of those aspects, I'm going to go to a different merge request. And this particular pipeline is running Code Sonar, which is a extensive C code analyzer for code quality and for security findings. And it does full flow analysis of the entire code base, makes a model of it. And so it actually monitors the build in order to do its findings. But when we run it as well as GitLabs, we find a bunch of findings here. And we can right in here drill into these findings. And in some cases, there will be training available, real-time training for the particular vulnerability. I think we might have it for this one. So that's an aspect of GitLab. And also within this vulnerability object, I can try to dismiss it. And I don't get to dismiss it automatically. This one does have training. I can create an issue if I need to collaborate further. You might be failing pipelines in order to prevent findings from moving forward. But in GitLab, we kind of consider that Stone Age now because we have this particular capability of preventing the merge with a rule. So this is a policy applied to many repositories that says if the developer is introducing a new finding of high or higher, then they need security approval or they need to go remove it. So at this point, I could go remove the vulnerable code and this would become optional. One other really important thing, these findings are only for the code I've changed. So this is not just a whole bunch of findings that are kind of, stuff that's been in the code for months, or we don't know who really added this. We're going to show it to you. Hopefully you'll take care of it. Because this is just for the code I've changed, then I know that I introduced these findings. So if I know I introduced them and I know if I fix them, I will not need to talk to anyone to merge this forward, then I have strong motivations to fix it. Most developers want to make really awesome software and do not want to introduce findings. So when you give them the right information at this point in the process, it's like with a physical device, all the parts are still on the bench instead of they're already, assembled together and tested together. So if you say, hey, this particular part is weak, it's going to break, it's going to have a problem, most folks will be just like, let me get that out of there right now because this is the right time. So this context of sharing work in progress allows you to approach critical software quality and security issues while the parts are still on the workbench. And people are so much more willing to dive into it at that point. Because if you say they have to update a board support package, now the compatibility of their entire solution is in question. Well, if they're still building and developing, they can qualify all of that and see if taking that new board support package, if it's worthwhile, or maybe it creates too much change and we have to seek an exception. So we can start working through those details at this level with lots of collaborative support. The other aspect here is for any scanners that are integrated with GitLab's scanning capability, and this includes third parties, when you come here into the overall panel, this is where we do see the findings that are in the code that have been accepted, and we click them, we can also explain or resolve with AI. So between the on-demand training and the AI, you can also help more junior folks be able to really get a better handle on what they might need to do to fix something. And if they fix it themselves, merge a new code, the scan comes up clean, that merge approval rule that we saw back here immediately becomes optional. So you can start getting better and better at security and code quality without having more and more folks in the security and code quality department. That's one of the main problems. If you scale this in a do-it-yourself framework, you end up scaling a role somewhere that has to run around and just pester people to fix things after they've already integrated and potentially shipped. So this is a much better mechanism and just one of the many benefits of sharing your work in progress. I'm not even really going to go into it, but on a merge request too, it'd be very typical to ask people for them to look at your code, and you'd start to get comments in here as well, human collaborative comments. And so that's a very interesting aspect as well. I'm just going to hop back to our slides to finish up here. So we talked about this model. We took a look at the work in progress savings. I just wanted to call out some resources here. The GitLab Embedded World resources are at the URL you see on the screen there. Within those resources, these are direct links, but within that first link, you'll find links to a self-paced proof of concept. Basically, the merge requests I showed you are out of a embedded workshop that you can go to GitLab and do on your own, and you can step through and see it in action and feel what it feels like for yourself. This workshop also starts with simply you using developer environment to build a binary and flash a board. So it starts with the normal everyday developer scenario of working with tethered hardware, and then you move on to all the further stages. Also, the on-premise device cloud is a component at GitLab, and so that link goes directly to it. I hope this is helpful. My heart goes out to all of you who are trying to get to those benefits of CI automation with embedded. I wanted to show you that GitLab is ready to help you with that all the possibilities of bringing hardware into the CI or the automation loop are available to you. I also wanted to encourage all of you, whether you're a developer or you manage embedded development, it's going to be important to drive into shared work in progress wherever you can. I do realize that you can't necessarily get away from hardware at the desk in every case, but embracing as much as possible to share your work is going to bring the value of DevSecOps in terms of people and process, as well as the technology value. Thanks for your time.